so where we left last time, we were talking about this moduli problem. So G is a reductive group. I'll just fix a base field of characteristic 0. This is a reductive group. I realize there might be some terminology. I mean, this G is an algebraic group made. X is an affine G scheme. And we were interested in the extended Hardy-Narasimhan theory to the following moduli problems. It's G of X. It's really, oh yes. C is a smooth projective curve. This moduli problem is the algebraic stack that classifies G bundles P over C plus and a section of the associated fiber bundle so this section, I guess I should, I wasn't so clear. Anyway, so or you can just think of this as a map from the curve to the quotient stack X mod G. So it's really, if vector bundles on a curve is the sort of, you know, first like archetypal moduli problem where you want to apply this. This is certainly sort of the next moduli problem. It would be just a curve and a G bundle and a little bit of extra data. And the question that I want to answer first is what does it mean if we're looking for a Hardy-Narasimhan filtration? Say, what is a filtration?
Wait, Dan, do you really mean X is an affine G, like affine?
It's affine, yeah. For this, yeah, like a vector, like a linear representation.
The map is the map from C to the. Okay.
The map from X. The section. Oh yeah, so it's twisted.
Okay.
So yeah, if it wasn't twisted, there wouldn't be interesting maps. Okay. Yeah, but with the G bundle, you can have when it's twisted by a G bundle, you can have non-interesting maps. Yeah.
It's one of the main points of this workshop, actually.
Yeah.
Affine. Okay.
So. Yeah, so actually I should say that the main theorem applies when X is projective over an affinization, but then you actually have to modify the moduli problem in a way that I'm choosing to de-emphasize because this is such a simple moduli problem. Andres is going to speak maybe more about like more complicated things about when X is projective and you have to go to more of a sort of go with the data set where you are curve and develop nodes, but. In this, so what is the filtration here? So there's a general answer to this. This is part of the introduction to theta stratifications. The answer is a filtration in an arbitrary. If X is an arbitrary stack, then a filtration. This is a definition. It's just a map F from A1 mod GM into X. So, or you can think of this as basically a GM equivariant map from A1 into the. So if X is families of some kind of X is the stack that parameterizes families of some object. So let me just say what this means. So this is. GM equivariant families over A1. So if you unpack what it means, if you use basically if you unpack what it means to have a map from a quotient stack into some other stack, if X is parameterizing families of some things, this parameter is equivariant families. So in the case stability literature, this is called a test configuration. But it's something that you can formulate for any mean, so an example, the baby example, and this is again an exercise for grad students. If you get, if you want to go somewhere else during the talk, you can try to figure out why A1 mod GM, a map from A1 mod GM. Oh, and this stack is so I call this stack theta. And the reason is because A1 mod GM the origin is fixed, so there's this point, and then there's just one other point that spins all the way around it. So it looks a little bit like a theta. And a map from this to BGLN is a z-weighted filtration of vector spaces. A z-weighted filtered vector space. So a map from A1 mod GM to BGLN, well, BGLN is the algebraic stack that parameterizes locally free sheaves. So it's asking what is a locally free sheaf on A1 mod GM, and there's a Riesz correspondence. This is the same thing as just a filtered vector space. And what I mean by z-weighted, finite dimensional filtered vector space. So there are basically finitely many jumps, but but it's weighted by integers. So the stack that we care about filtrations in MGX. So these will be. And again, it's not a definition, it's just unpacking this definition. It's a z-weighted filtered vector bundle. Oh, sorry, filtered. Well, oh yeah. Let me just do the GLN case. I mean, in general, it's like a parabolic reduction, but in this GLN case, it's a z-weighted filtered vector bundle. And so on. So let me call the colimit here E. So what this has to, so what I mean by this is that, what I mean by a filtered vector bundle is that, so it stabilizes to 0 on the left, and it stabilizes to some vector bundle on the right. And the associated gradients of all these inclusions are also vector bundles, are also locally free. And a section of the associated fiber bundle that's compatible with the filtration. So there's a general way to say this, but in examples, it's usually just clear what the compatibility means. So it's a z-weighted filtration. So in the example of I don't think I gave this a name, but in the example of this thing algebras over C. So this is the one that corresponds to So in the example that I talked about where you think of a pure dimension 1 scheme with a finite morphism to C, and I said, well, that is really the same thing as just, it's always spec of whatever the push forward of the structure sheaf is. So it's spec of some coherent sheaf of algebras over C. And so you can think of this sort of more geometric problem as kind of a vector bundle plus extra data. So it's not coherent, I guess locally free. So you can think of it as a vector bundle plus some additional data, which is the structure of an algebra. So there's a multiplication map. So, basically this is a vector bundle E, and the additional data of a map from E, tensor E to E, and also, so this is the multiplication map and an identity section satisfying relations. Right. So in this case, if you have a filtration of the underlying locally free sheaf, what does it mean to be compatibility? So in this example, compatible means what you might guess if you were to try to guess the definition of a Z-filtered algebra. It means that if I take EW times EV, that should be, the image of this in E should be contained in EV plus W. And also the identity section, E, should be a section of E0. So there's this sort of abstract definition of what is a filtration, a map from A1 mod GM, and in this particular example, if you unpack it, it gives a reasonable notion of what would be a Z-filtered, coherent, or locally free algebra over C.
So the section, can it lie in like E1 or?
Yeah, I guess so, yeah. But probably
But then the gradient might not help.
yeah, it probably, yeah. You might get something weird if it lies in E1. So then, maybe then the algebra would have to be 0 or something, because then powers of it would have to lie in E2, E3, E4, E5, and that eventually stabilizes to 0. So it would be saying that the unit is nilpotent. So I think that would give you. I think probably what you find is that
The filtration's unbound. Like you have it in both directions.
it's not. It's unbounded, but it stabilizes to 0 on the left, and it stabilizes to a vector bundle on the right. Probably these conditions would rule that out. Yeah.
So I'm a bit confused about what you wrote. So the filtrations in MGLN is a section that's compatible with filtration, but here you explain what the compatibility means for the map M and not for the section E.
No, sorry. Compatibility is what does it mean for the filtration. So the section of the associated bundle is this additional data. So I have a vector bundle. This is a section of associated bundle. The associated bundle was E plus HOM of E tensor E to E. Right. Right. Yeah. So this is this moduli problem is always like a G bundle plus some data, and the data is always a section of some associated fiber bundle. And that's this. Yeah. So that's specified on the limit here. But what does it mean for the filtration to be compatible? And you see, the Z weighting kind of arises naturally here. If you just had a non-weighted filtration, you're asking what does it mean for the filtration to be compatible with an algebra structure? It's like a little bit. You end up wanting to use the indices. It's not like an unweighted filtration doesn't really make sense to ask what it means to be compatible with an algebra if you think about it for a little bit. Okay, so now we're trying to extend Harder assimilant theory to modular problems like this. So what is a theta stratification? this is again a sort of abstract definition. So this is the generalization of the Hardenauer-Simon filtration of the Hardenauer-Simon stratification of the moduli vector bundles. I mean, it's a formal concept that generalizes the key property here. Yeah. So basically, to answer this question, I have to say, so this given an algebraic stack X, the stack filt of X, this is what's called the mapping stack from the stack theta, which is A1 mod GM, into X. So by definition, so a mapping stack is a sort of general formulation that you can make, but basically a T-point, a test scheme T, what does this stack parameterize? It parameterizes families of maps from A1 mod GM, or in other words, it's the map from A1 over T mod GM over T into the stack X. So again, if X is parameterizing kind of families of some kinds of objects, this is like a T-point of this stack is a family over A1 times T, that's GM times T equivariant. And in some large generality, this is also an algebraic stack. So the idea is that the points over the ground field are just what I'm calling filtrations. But you can talk about now algebraic families of filtrations. And now, if you think about it, right, I mean, a filtered, in this example here, like what is a family of such filtrations? Well, there's some discrete data, which is sort of locally constant in families. So I have this filtration of vector spaces, and it stabilizes to 0 and stabilizes some finite dimensional thing there, or I guess dimension n. And so there are finitely many jumps. So you can think of this as a z-weighted filtration, but another way to think of it is an unweighted filtration, just a filtered vector space along with the data of where the jumps happen. So it's like another way to think of, and that's a convenient thing here too. You can think of this as like EP, inside of EP minus 1, inside of E0, which is what I'm calling E, along with some data, which is where this jump happens, where this. So you can think of this as just as an unweighted filtered vector bundle along with some integers that are ascending sequence of integers like this. And so those integers in an algebraic family, those integers will not change. And so there's many connected components. This mapping stack is somehow huge. It's many connected components. Each connected component, though, in other words, if you keep these integers constant, if you fix the weights, then you're just talking about a varying of filtration. And as we know, filtrations of a vector space, unweighted filtrations, have sort of moduli, like they're parameterized by a flag scheme. So basically, you're recovering the flag scheme modulo GLN. Or another way to say that is the classifying stack of a parabolic subgroup. So this stack of filtered points of BGLN is just a sort of infinite disjoint union over all of choices of weights like this of the classifying stack of the corresponding parabolic group.
Can you remind me what the condition is for it to be algebraic?
For a stack to be algebraic?
No, for the mapping stack to be algebraic.
Oh, well, I mean, so there's a general theorem about this.
Wait, what's the, it's a
So if
stack, sorry.
X should be like, over, let's say, a field or some Noetherian base, it should be locally finite type with affine automorphism groups. Yeah. And if you want things even nicer, it should have also what's called separated inertia. But I think just to be algebraic, it's just locally finite type with affine automorphism groups. So basically, all the kinds of moduli problems that arise and that look kind of like their global quotients. They kind of look like their local quotients, but not necessarily. So moduli have like polarized varieties is fine. So anyway, a theta stratification, the reason why, previously I said that the Harder-Simhan stratification is just a locally closed stratification of the stack of bundles. That's not quite the complete story, because the strata have modular interpretations of their own. So the strata is not, the strata in the stack of vector bundles, it's not just the locus where the Harder-Simhan filtration has a certain shape. It's actually, they have a modular interpretation as parameterizing a vector bundle along with the Harder-Simhan filtration. So actually there are the Harder-Simhan filtrations exist over a particular stratum in a nice algebraic family. And so that's the thing that this theory captures. So basically, the data stratification is just an open substack S inside of this stack filter X. With connected components as alpha ordered in such a way that oh yeah, I should. So this stack of filtrations, there are various kind of things that you can do to a filtration, right? And I should have mentioned this before, but given a filtration F, so a filtration is really just a map from A1 mod GM to X, and A1 mod GM has 2 points. It has a point 1 and it has a point 0. So I can take this to F of 1. And that's like the underlying, in the examples that I've erased, or in this example, if I think of this under the correspondence where this is really just a map from A1 mod GM to this stack, if I take the image of the 1, that is just E, forgetting the filtration. So this is the map that forgets the filtration. So this is a map evaluate at 1, and it takes the stack of filtrations in X to X. This forgets the filtration. Does just take the fiber at 1. And if I take the fiber at 0, you know, so f of 0, I should say, is the associated graded. I guess it's sort of useful to have this in mind. When you're thinking of a map from A1 mod GM as a filtration, the image of 1 is the underlying object, 0 is associated graded, because again, in A1 mod GM, the point 1 has nothing, but the point 0 has a GM worth of automorphisms. So f of 0 has canonically inside of it, has canonically a GM that acts on it. And that's why you think it's a graded object. It's like a vector space with a GM action is a graded vector space. And so basically, this is just you know, expanding on this analogy. I call this mapping stack filtrations. But the point is that in this, I have this evaluation map, and I can restrict it to each connected component, and this should be a locally closed immersion. And basically, the images should basically give a nice So basically, I can identify S alpha under this map. I can identify S alpha is sort of S alpha is canonically identified via this map with a locally closed substack of X. And this is basically the thing. You know, for the stack of vector bundles, you have the stack of filtered vector bundles, and then you have the forgetful map for the filtration. So this is actually saying that if you inside of the stack of filtered vector bundles, you can consider filtered vector bundles which happen to be Harder-Simhan filtrations. Right, so the Harder-Simhan filtration was just this convex filtration whose associated graded objects are semi-stable. So inside of here, there's a substack like that. It's filtered vector bundles. I have to tell you what the weights are, but basically it's filtered vector bundles that are convex, whose associated gradeds happen to be semi-stable. And the Harder-Simhan theorem is saying that there's basically a unique filtration of that kind for every unstable bundle, and that's basically saying that this map is injective. If you happen to restrict to the locus of Harder-Simhan filtrations, the filtration itself, which exists here, is actually uniquely determined by the underlying vector bundle by forgetting the filtration. So the Harder-Simhan theorem is somehow saying that this map, this forgetful map, if you restrict to just Harder-Simhan filtrations, the forgetful map becomes a local immersion. That's what the Harder-Simhan theorem is saying. And I mean, in addition to other things. But so this is the generalization. So this is a locally closed immersion, and the images should stratify. So basically, the alphas are ordered, and the closure of S alpha should be contained in the union over, like, you know, sort of, you know, more unstable strata. Oops. So the idea is that you have a bunch of connected components to the stack of filtered points, and they're sort of ordered in a way so you have more and more unstable. In the case of Harder-Simhan filtrations, the ordering has to do with like how large that convex set is for when you plot the ranks and degrees of the subquotients. You get larger and larger and larger polytopes. And there's some, you know, the stratification condition says that the closure of the S alpha. So S alpha is actually a closed immersion in the complement of, once you remove the higher strata, S alpha is actually a closed immersion. That's what this is saying. You remove the higher strata and S alpha is a closed immersion.
Is the ordering automatic given the structure inside filtex, or is it?
No, it's not automatic. Yeah, so it's not automatic. I mean, maybe it's automatic if you identify an open substack. I guess, you know, this gives some constraints on how they can be ordered. But yeah, it comes from additional data, which I'll tell you about. So So this is, because this is called Introduction to Theta Stratifications, I'm giving you a sort of a general abstract definition of what is a theta stratification. But keep in mind that in the example that we care about, it really is basically the same thing as the Harden-R symbol. It's some canonical z-weighted, it's some stratification of the stack where the strata themselves have a modular interpretation as, in this case of a coherent algebra with a compatible z-weighted filtration. So it really is not that, in the examples, it's not that far away from a Harden-R-Simon filtration, from the Harden-R-Simon stratification. But I guess I should point out why this is tricky to do. I mean, why all of this discussion? You have a canonical filtration of the underlying vector bundle. You have the Harden-R-Simon filtration of this vector bundle on C. Right. But it's just that it just might not be compatible with this additional data. And so once you're looking for filtrations that are compatible with this additional section, you're basically at a loss, because it's, how do you even write down a filtration like this, and what does that possibly, what relation could that possibly have with the Harden-R-Simon filtration? There might be no relation. So in some examples where this structure is known, like in the example of Higgs bundles, like it's sort of, you get something that's kind of similar to the Harden-R-Simon filtration. You get a nice convex filtration, but in general, these filtrations don't have to be convex. So it doesn't really have to look like what you're, and in fact, the construction of these filtrations ultimately cannot be carried out the same way that the Harden-R-Simon filtration is constructed for vector bundles. And for vector bundles, it's constructed by like an inductive procedure. And you're really using the fact that that you're basically objects in a k-linear category. So you can say, okay, we'll take the maximal destabilizing subbundle, show that exists, and then take the quotient, and now look at the Harden-R-Simon filtration of the quotient, and da-da-da-da. But that kind of stuff doesn't exist. That doesn't work when you start to decorate your vector bundle with extra data. So, okay. So even though the theorem that I'm working towards looks very similar to the Harden-R-Simon theorem, very different methods are needed, basically, which is what drives us to this sort of abstract formulation. So if you're trying to rediscover the Harden-R-Simon filtration and you're not trying to use the theory of like additive categories to say take a maximal subobject, think words like that, how would you find it? And so where does this come from? So in other words, how are you supposed to get this ordering? How are you supposed to discover these canonical filtrations to begin with? So basically, given a line bundle, L on X, then you can define this function. Well, and a norm on filtrations so right now I can be more precise what I mean by norm, but basically I mean you have a filtration F, and the norm is just some real number, that's positive for a non-trivial filtration. You can define a function mu that takes a filtration F to, so the weight of the line bundle F star of L divided by the norm of F. And so I guess in case people are getting lost in the notation, right? So,
What's the meaning of openness? Like, why does it have to be an open substack? Like,
Well, I mean, I guess there are actually there are other formulations there are other formulations, you know, well, you want it to be an algebraic stack. So an open substack of filters is algebraic, and you know, I don't know, the openness, it just sort of I don't know. I mean, maybe it's a longer answer than I want to get into.
Yeah.
But another way to think about this is that, like I said, that the closure of this S alpha lies in if you take the complement. So another way to define it, the way I actually define it in the paper, is like if you, it's a stratification by larger and larger open substacks of X. Stratification is it's a sort of filtration by open substacks, so that, you know, the difference between one open substack and the next is a union of individual theta strata, and a theta stratum is an open and closed substack of the stack of filtrations. So, but I don't know, if you want to formulate it exactly on X, then it just becomes an open substack. Yeah. Right. So a theta stratification with exactly one stratum is just an open and closed substack of the stack of filtered objects, such that the map is a closed immersion. Yeah. Okay, so right. So if you have a line bundle on X, so I can pull that line bundle back to A1 mod GM, and a line bundle in A1 mod GM is just, I mean, it's entirely determined by just whatever the character that you get at the origin. So the fiber at the origin has some character, and that character so you get some weight. So this is a weight. This is an integer, and this is a real number. Yeah, so this is a real number. So this is very much like the normalized Hilbert-Mumford numerical invariant in geometric invariant theory. It's exactly the same, actually. It's a generalization of the normalized Hilbert-Mumford numerical invariant, where you take the weight of, so you have some GM equivariant family, so you can think of the point A1 as sort of limiting to the point 1 is limiting to the point 0 in X, and the point 0, the image of 0 has this GM automorphism group, and I can ask what is the fiber of this line bundle at the image of 0, and what is the weight of the GM action on that fiber? And that's this number here.
Sorry, can you say again what is a norm on filtration?
Well, yeah. Let me just give. So what I want is basically. I'll say it in a second, okay? Yeah. So, I'm not sure if this is helpful, but like the examples well, no, this won't be helpful. Let me just say. So the key properties, well, I'll say it. So, like the example that will happen here is if you have a class, so I can think of, this is something really that just corresponds to the cohomology class. C1 of the line bundle. C1 of the line bundle will already tell you what the weight is when I pull it back here, and I look in the second cohomology of this thing is just one-dimensional, and so I get a number when I pull back the line bundle. If I take the fourth cohomology here, H4 of this stack, and I pull something back, I also get H4 of this is also one-dimensional. It's just the cohomology of C infinity. It's the cohomology of BGM, and so if I take a class in H4 and I pull it back, I get just a number. So the examples that arise for us is I take the square root of the pullback. I take the pullback B and I take the square root where B in H4 of X, it should be sort of positive definite in the sense that it's this number that I get is always positive. So if I have a particular kind of cohomology class on X, now I'm imagining just working over the complex numbers and I'm using usual cohomology. So if I have a cohomology class in X and H4, I can pull it back and can find a positive definite one where this number is always positive, and then I take the square root. That's a norm. That's the examples that I'm going to tell you arise that way, yeah?
And like the quotient stack examples, is this basically just like a norm on the Lie algebra?
Yes. So in GIT setting in the quotient stack, it's a norm on the Lie. It's like a Weil group invariant norm on the co-character lattice for the group. I mean, yeah. So I didn't quite say it, but this is a quotient stack. These connected components basically are indexed by co-characters of the group G. And this is just the norm of the co-character. Okay. But I don't want to, yeah, so, right. So the key properties of this thing, let me see, check my time. I have no time. So definition, X and X is unstable if there exists a filtration with f of 1 equals to x and mu of f positive. So this is like so basically this is the Hilbert-Mumford criterion. Now the positivity just has to do with, it doesn't have to do with the norm, that's just a positive real number. So the positivity has to do with the weight of the line bundle. So the notion of instability really just depends on the line bundle on the stack. And the Harder-Narasimhan filtration is defined to be a filtration that maximizes that number. So a HN filtration of an unstable point is a filtration where the mu of f is equal to, well, let's choose a function, mu of x one. So if a filtration that realizes the supremum over all filtrations of a particular point x is called a Harder-Narasimhan filtration. And this function, which assigns any point to the supremum over all the value of the numerical invariant over all filtrations, is sort of measuring how unstable a point is. So now let me leave the abstract for a bit and just in our example here. So in our example, there is a line bundle, a nice tautological line bundle on the stack on mg of x. On the stack mg of x, there are nice line bundles. Basically, it's some combination of the determinant of cohomology coming from the adjoint bundle associated to this G bundle. So it's basically the theta divisor gives you some line bundles for the underlying. The theta divisor for the underlying G bundle gives you a nice line bundle here. And then there are also line bundles you can induce on this thing from equivariant line bundles on X itself. So you can produce these line bundles, but what you end up getting is the following. So mu of a filtration F. So remember my filtration. It's just a, you know, it's filtration is really just a filtration of the underlying vector bundle, and it's going to have the form. There's some linear form. Let me do my GLN. Plus something coming from X itself, from the line bundle that you choose on X, and divided by the square root of B, a quadratic form where L1. So this is the thing coming is the following. It's the sum over W in Z of W times the degree of GER W of E minus so if you look at if you have a filtration like this and you look at the weight of like the theta divisor coming from bun GLN, then you get this formula, and the LX, what you get is, so I'll get so this is really the Hilbert-Mumford weight. So, but in this case, let's say you choose, you know, my group is GLR, and so if let's say that I linearize my action by just OX tensor with the character determinant to the M. So if I linearize my action by some line bundle, that's part of the input to GIT. Then the Hilbert-Mumford weight here is just going to be M times the sum over W of W times the rank of GER W.
Can I see the lower indices on E?
There's no, this is, sorry, this is GER. So E is like the filtration itself, and I'm taking the GER W, the Wth graded piece. Yeah, so this is take the graded pieces. So this is it looks infinite, but it's finite, because only many of these graded pieces are non-zero. Yeah. Or another way to say this is that if you think of it as an unweighted filtration along with weights, choices of weights then this is just this for each of the graded pieces times the weight where it jumps. So you can write this explicitly as a finite sum, and the norm here is the square root of the sum of W squared times the rank of the associated graded pieces. So if I think of this as a function of, if I think about fixing the actual bundle and letting the weights vary, oops, okay. Yeah. If I think of that this is as a fixing the underlying unweighted filtration and just letting the weights vary, this is a linear form in the W. This is the linear form in the W's, and this is the square root of a rational quadratic form in the W's. And so the key feature that this function has is that if I fix the filtration and now just vary the weights, there's actually a unique maximizer. So that's like a theorem. I learned this theorem when I did an internship at a hedge fund, and because this is what they use for portfolio optimization all the time, where they have
Is it clear that in general it exists? I mean, it's a, I guess it is.
No, not at all. Right. So yeah. So let me just state. I'm sorry. Can I take like an extra? I don't know who's. Oh yeah, you're the chair. Can I take an extra 2 minutes or something to finish it? Oh yeah. Yeah. So the main theorem. So yeah. So basically, the general theorem is that if you have a function of this kind, I should say the key property of this function, the single most important property, is that it's locally constant on the. It only depends on the weights of the filtration in this example. It only depends on the weights. It doesn't depend at all algebraically on the filtration. And that's the key. That's the key property. So it's a locally constant function on the stack of filtered points. So a function mu as above determines a theta stratification if it satisfies two properties. So one is called strict monotonicity, and two is called HN boundaries. And furthermore, if the semi-stable locus, so part of the theta stratification, part of this closure condition says that if I take all of the unstable strata, their complement will be an open substack, which is the semi-stable locus. And so if I take, furthermore, if X semi-stable is bounded, it admits a separated good moduli space. And that's proper. This is proper if X satisfies the existence part of the valuative criterion. If X itself. In other words, yeah. So this basically is this theorem is sort of the main replacement in the intrinsic setting of the main theorems of GIT. Basically, it's saying that if you have a function of this kind, like weight of the line bundle divided by a rational quadratic norm on filtrations, then you want to know, does everything work? In other words, do you get a nice stratification? So when I say determines this theta stratification, what I mean by saying this is that the Harder-Narasimhan filtrations pick out points. The Harder-Narasimhan filtrations pick out some subset of filter S, and then maybe that's an open subset, and has these nice properties. So I can ask, when did the Harder-Narasimhan filtrations, as defined here, determine a theta stratification? And when does the semi-stable locus have a good moduli space that's separated and possibly proper, if you started with the stack that already has it? And so the theorem says basically there are two conditions you have to check. And I haven't told you what they are yet, but one is called strict monotonicity and the other is HN boundedness. And so both of these conditions are automatic in like projective GIT. So that's why if you have a projective monoreductive group, that's why, and if you take an ample line bundle, everything works really nicely. These two conditions are automatic, very easy to check.
What is evaluative criteria?
I mean the existence part of the valuative criterion. So if you have a family if you have a DVR and you have a point over the generic point, if you have a point in the stack over the generic point, it extends over the whole DVR. If you have a family of vector bundles if you have a vector bundle over the fraction field of a DVR, you can extend it to a family over the DVR. In some non-unique way, but yeah. So if you just have, if you prove this extension result, which is, so in examples, sometimes it's easy to do this for the stack, but the semi-stable locus is not so easy. I mean, vector bundles is an example of this. If you take vector bundles over a curve, this extension, you can extend over a DVR, but this special fiber might not be semi-stable anymore. And then you use this Langton's algorithm to, to show that you can modify it so that the special fiber is semi-stable. So anyway, so in examples like Bun of the curve, checking these two conditions becomes much more interesting. And so the theorem that I'm going to tell for is that this numerical invariant and this is where I'll pick up tomorrow on MG of X satisfies these two conditions. So I have to tell you what the conditions, I'll tell you specifically what the conditions are, this monotonicity and the HM boundedness, and I'll explain why in this particular moduli problem that satisfies these conditions, and so you get the whole GIT package just directly on the stack, where you get a semi-stable locus, and you get a stratification, a Harder-Simon stratification. Okay, sorry for going over a little bit. Thanks.
We have time for a couple of questions.
Sorry, I got a little bit confused when you started talking about the notion of unstable. But just to compare to like the usual case of Bun RD that you talked before, in that case, this line bundle determinant would be determinant line bundle.
The determinant of cohomology would work.
In this function mu. This function mu is what? It's like degree of biggest subbundle.
No, it's this.
It's sub of degree. Okay.
It's this. It's actually a crazy function. I mean, well, okay. So yeah, I've said it in words, but this is not how the Harder-Simon filtration is characterized in the actual development of the. This is not historically. This is not how the Harder-Simon.
So this L bun also works for a bun.
Yeah. This is like the pullback. Underlying this thing, there's a map to Bun GLR. And I'm just saying, pull back the line bundle from Bun GLR that you use to define stability of the line bundle of the underlying vector bundle, and so you get this strange function which depends on the whole filtration. And so actually, one of the consequences of this existence and uniqueness is not just that there's a Harder-Simon filtration that is unique, but also it comes with canonical weights. The W's are also sort of and I should say that this numerator is homogeneous of degree 1 with respect to scaling. So you can take the filtration and just rescale the weights where the jumps happen, and that will just scale the weight by the same amount. But then the norm on the filtration will also scale. So this ratio, the reason why I put the norm there is so that you can't make this number arbitrarily big by rescaling the weights. That would be kind of silly. But as a result, you only get a unique maximizer up to rescaling the weights. So in the case of the Harder-Simon filtration, the weights where the jumps happen are proportional to the slopes of the associated graded pieces. But that's not a definition that comes out of this optimization problem. So I find this very crazy, actually. The idea is that every weighted filtration, z-weighted filtration, you can assign a real number. And I mean, because keep in mind, not only are there infinitely, there's sort of algebraic, there are uncountably infinitely many ways of filtering a vector bundle. And so it's just saying that there's just this one real number, and there's a unique filtration that maximizes it, and that's the Harder-Simon filtration, and it picks out these weights, which are the slopes.
I see.
So it's actually a very
and how does it being?
strange.
Is it easy to see that it being positive means you have a destabilizing subobject?
That is much easier, yeah. Because just to find some filtration where it's positive, you can restrict to two-term filtrations. And the usual notion of semi-stability for vector bundles is phrased in terms of just a subobject that's so you can look at this. If you look at this number, that's another little exercise. If you take this number, you can check that if you have if you just take a two-term filtration with some choice of weights, it doesn't really matter. A two-term filtration where the subobject has larger slope, this number will be positive. And if you have less slope, lower slope, this will be negative, so it won't be destabilizing. So yeah, for the notion of semi-stability, it's pretty easy to check that.
Yeah, well, we should stop.
Sorry.
Time.
Yeah. Well, I guess other questions
You guys
I can
continue the
take
discussion
later.
later.
Yeah.
Okay, let's take the speaker again.